you had the full white light spectrum of the sun, and because it's a glass medium, you have the possibility for prismatic refraction. You have prisms. Each glass shard is going to be a prism, and it's going to refract red light differently than blue light, so you're going to get rainbows. One of the key scientific elements of fundamental science is called the art of scientific prediction. A model is only as good as what it can predict based on how it's constructed, and then you go and you observe more, and if you find an observation corresponding to the prediction of the model, that's basically the only way you know that you're on to something that's true. You don't have science unless you have prediction, successful prediction. So as I'm going through this, I'm starting to think, okay, one of the key, most exciting predictions of this model is that not only are we looking at glass structures, but we ought to be able to see in certain angles and certain geometry with the sun, prism-type effects from the glass structures sticking up from the ancient lunar domes. So I started looking. This, by the way, is how a prism works. Light comes in, is differentially refracted, so you get this rainbow prismatic effect. And lo and behold, on this particular frame, and I'll show you which one it is in a minute, located, I think, right above here, when I brightened it up and I zoomed in, there is a stunning prismatic dispersion column. Now, notice it's from the grid. It's from this geometric grid of vertical stringers and horizontal crossbars that has, it's denser over here than over here. This is toward the sun. This is away from the sun. Remember, the farther away from the sun, the more the scattering, like the movie screen effect. So everything is consistent to a real grid, and in the middle of this square, enlarged down here, there is this incredible, beautiful prism effect hanging in the middle of what should be a totally pitch black vacuum lunar sky. There is no other explanation. There's no mundane way to explain this away than there is a real chunk of glass suspended in this grid at just the right angle to reflect and refract the sun, which is coming in from screen right over here, and to reach the camera of the astronaut who took the picture. And here's a close-up. Notice this exquisite rainbow, and notice it's a bar, and it's tilted away from the vertical. Now, in subsequent analyses, we found other examples. The reason, by the way, it's showing up is because the Ektachrome film on which these pictures were taken has red, green, and blue layers, and when you reverse them, they're actually cyan, magenta, and whatever. You reverse them, you get red, green, blue, so that's how you record color, approximating the human eye. So, of course, you were going to record spectra if they are there. Now, these are the two frames. This is this frame number, and this is this frame number. And what we've got is prisms in both frames over the same hill, or whatever. And here is the comparison of the second one. Notice that it's lying at a flatter angle, all right? And we compare, see, the angle is lying down more, different angle to the sun, different angle to the camera. We then compare them side by side. Here's the first one I showed you. Here's the second one. So they're not identical, but they are. They're obviously the same physical effect, but there are different places in the dome correlating with the geometry of sun, glass chunk, camera, and there is no way this can be explained except a real physical object scattering light. Now, this is one of my favorites, all right? Here's a puff piece. This is a PR shot showing astronaut, American flag, Earth, and this is CERN. So Schmidt was taking the picture. The red stripes are the commander's red stripes. Here's the enhancement. And then we magnify, and right next to the Earth, from here, there is a vertical stringer. And notice the reflections and refractions both above and below in the layers of glass of the dome. I mean, if you want a smoking gun example of why this has to be real, there's no other explanation. This is it. Except, I've got a better example. And this one is so cool. Well, take a look. This is now Schmidt, the unenhanced regular picture, and you can see that there's all kinds of interesting shadings of color on the spacesuit, but back here, can everybody see back here that there's something interesting going on? If you can't, we can zoom in, because there is a set of horizontal color prism-like bands all along the horizon beyond the mountains. And if we do a close-up in here, this box.
Hey Richard.
Yes.
Could you put your laser at the screen on the right, just for camera?
Over here?
Yeah.
Okay. If you take this box and you zoom in, you'll see that there is a prismatic shard right here, almost horizontal now, because you're looking opposite the sun. The sun is behind you, and you're looking almost directly opposite. So there's a correlation between the angle to the vertical and the horizontal, depending upon the angle between the sun and the glass shard and the camera, and it's bouncing it directly back. Now, it gets better. If you look at this picture, you'll see that this brightness, and there's too much scattered light in here to really see this, but there's red tinging to green, tinging to blue up here, beyond these hills, beyond these mountains. It's something in the sky which is like a sunrise or sunset on Earth is scattering back the prism of the rising sun to the east behind the astronaut taking the picture, who in this case was Gene Cernan, Mr. Unhappy. This is a photograph of the Golden Gate at sunset, showing the same effect on Earth. You have an atmosphere, you have an optically active medium. It's over here, it's refracting light. Here, it's scattering light. So you get red near the horizon. Then you get green, greenish yellow. Then you get green. Then you get blue. In other words, it's a prism band. And the only reason you're seeing it on Earth is because you've got an atmosphere for this light to be scattered back from. It's kind of like a semi-transparent movie screen, and clouds help. All right, the clouds become, part of the scattering medium. Okay, here's the comparison. Here's Earth, Golden Gate on the right. Here is the lunar equivalent on the left. This is impossible unless there is an active optical medium extending above the horizon, scattering the prism effect from the rising sun on the opposite side of the camera. This is the shadow. This is Cernan's shadow, the tip of his head, okay? Behind the guy who takes the picture. So this is looking down sun. This is looking away from the sun. And notice this is the actual direction of the sun. So we're just a little off, and that's why it isn't perfectly horizontal. It's tilted at some angle, that little prism in there. This to me, all right, this is another version. This is again the astronaut. This is Cernan. Here's the lunar module. Here's South Massive. Here's the regular shot. Here's the brightened shot showing the prismatic color array in the sky behind the mountain. If this was a photographic defect, it would be coloring everything. The band would go across everything. It's not. It's in the optically thin material stretching hundreds and hundreds of miles, like looking through the atmosphere at sunset or sunrise. You're looking through hundreds of miles of air, which is why you can see it. This is the smoking gun of the active, optically glass-like lunar dome model. Enough of it surviving so it produces amazing color